permutation statistic that's similar to descents is called excedances. It's similar in the sense that we measure descents in a permutation to see, in some sense, how far away that permutation is from the identity. The identity permutation doesn't have any descents, and every time we see bigger letter before smaller letter, we know that we're in a permutation that is different from the identity permutation. Similarly, excedances, the identity permutation has 0 excedances. Let me put the definitions up on the board. First of all, let's recall the definition of descent. So recall that I is a descent in a permutation W if Wi is greater than what follows it, Wi plus 1. And similarly, we can say I is an ascent of W if Wi is less than Wi plus 1. Then DES of W is the number of descents in W. And we can let ASC of W be the number of ascents in W. Which is n minus 1 minus the number of descents. Because at every position, we have either that the next letter is greater than or smaller than the letter in the position that we're looking at. Now let's call I an exceedance in W if Wi is greater than I. And we can call I an anti-exceedance if Wi is less than I. Now these are not exactly complementary the way ascents and descents are, because at every position we certainly have an ascent or we certainly have a descent. Here, if Wi equals I, we have neither an exceedance nor an anti-exceedance. So let's make a table for S3. So the permutations are 3, 2, 1, 3, 1, 2, 2, 1, 3, 2, 3, 1, 1, 3, 2, 1, 2, 3. The number of descents are 2 because 3 is bigger than 2, 2 is bigger than 1, 3 is bigger than 1, 2 is bigger than 1, 3 is bigger than 1, 3 is bigger than 2, and then 0. The number of ascents are 2 minus the number of descents. So there's no place where we're going up here. 1 is less than 2, so that's 1 ascent. 1 is less than 3, so that's 1 ascent. 2 is less than 3, that's 1 ascent. 1 is less than 3, 1 is less than 2, and 2 is less than 3. So again, the sum here is going to be 2 every time if we add up descents plus ascents. The number of exceedances we can find by comparing the letter in position I to I itself. So we say is 3 bigger than 1, is 2 bigger than 2, is 1 bigger than 3. Well, 3 is bigger than 1, so we have 1 exceedance here. 3 is bigger than 1, 1 is not bigger than 2, 2 is not bigger than 3. Again, 1 exceedance. 2 is bigger than 1, 1 is not bigger than 2, 3 is not bigger than 3. So again, 1 exceedance. 2 is bigger than 1, 3 is bigger than 2, 1 is not bigger than 3. So again, we have So now we have two exceedances, positions 1 and 2. 1 is not bigger than 1. 3 is bigger than 2. That's 1 exceedance. And here we have 0 exceedances because 1 is not bigger than 1, 2 is not bigger than 2, and 3 is not bigger than 3. No, I didn't define the notation. EXC is the number of exceedances. AEXC is the number of anti-exceedances. So the number of anti-exceedances, now we're looking for letters that are smaller than their position. 3 is not smaller than 1, 2 is not smaller than 2, but 1 is smaller than 3. 3 is not smaller than 1, 1 is smaller than 2, and 2 is smaller than 3. So 2 anti-exceedances. 2 is not smaller than 1, 1 is smaller than 2, so that's 1 anti-exceedance. 2 is not smaller than 1, 3 is not smaller than 3, but 1 is smaller than 3. 1 is not smaller than 1, 2 is not small, 3 is not smaller than 2, but 2 is smaller than 3. And then 1 is not smaller than 1, 2 is not smaller than 2, 3 is not smaller than 3. So 0 anti-exceedances. So we can see that exceedances plus anti-exceedances don't add up to 2 all the time. So EXC of W is the number of exceedances. And AEXC is the number of anti-exceedances. Now the distributions on S3 of all 4 of these statistics are 1, 4, 1. We see the value of 0 once. We see the value 1 4 times. We see the value 2 once. And in fact, all 4 of these permutation statistics are equally distributed on Sn for any n. The distributions on Sn of descents, ascents, exceedances, and anti-exceedances are the same. So we say they are equally distributed. And sometimes when 2 permutation statistics are equally distributed, we can define an equivalence relation on permutation statistics by saying 2 statistics are equivalent if they're equally distributed on Sn for all n. So we can write, let's say, stat 1 twiddle stat 2 if these 2 statistics are equally distributed on Sn for all n. So to prove this, well, descents and ascents are easy to prove. So these are equally distributed because we have that the number of descents in in W reverse equals the number of ascents in W. And sending W to its reverse is a bijection. Now the proof that exceedances and anti-exceedances are equidistributed is almost as easy. So we claim that the number of anti-exceedances in W is equal to the number of exceedances in W inverse. And of course, sending a permutation to its inverse is a bijection from Sn to itself. So first observe that I is an anti-exceedance. Position I is an anti-exceedance of W if and only if I is greater than Wi. But in one line notation, W inverse has not, well, since W has Wi in position I, W inverse has I in position Wi. So that means that the inequality I is greater than Wi is equivalent to I is whatever W inverse has in position Wi. So that's just I. So that is greater than Wi. But if what we see in position Wi is greater than the index Wi, that means that we have an exceedance. So position Wi is an exceedance of W inverse. All right, now the substantial part of the proof is showing that descents and exceedances are equally distributed. So we'll look at descents and anti-exceedances. Let's let sigma be the parenthesis erasing bijection that we looked at last time. And let's write W in standard cycle notation. As A1, maybe I'd better do this bigger. And let's use the index I1 for whatever is the end of that cycle. Then we'll have AI1 plus 1 through AI2. And the last cycle is going to be AI. Let's say if there's k cycles, then the kth cycle is going to end at AIK. Sorry. Yeah, if there are k cycles, the last cycle is going to end at AIK. So the second to last cycle is going to end at AIK minus 1. And the last cycle is going to start at AIK minus 1 plus 1. And of course, by the time we get to the kth cycle, well, we know how many indices there are total. There's n. So AK is going to be AN. Sorry, that's AIK. IK is equal to n. And then that forces us to write sigma of W as exactly this sequence of letters, but with no parentheses. A1 through AI1, AI1 plus 1 through AI2, etc. up to AIK minus 1 plus 1 through AIK, which is AN. Alright, so we're claiming that descents and anti-excedances are equally distributed. So let's suppose that J is a descent in sigma of W. So that means that AJ is greater than AJ plus 1. And AJ, in W, AJ does not appear last in its cycle. So what appears last in a cycle is definitely going to be less than what appears first in the next cycle. Also, I guess we can't have a descent if we're all the way at the end. If we're at AN, there is no AN plus 1. So AJ is greater than AJ plus 1, and AJ does not appear last in its cycle in the standard cycle notation of W. So that means that AJ and AJ plus 1 appear consecutively. In a cycle of W. And AJ is, we said it's a descent. So AJ is greater than AJ plus 1, which equals W of AJ. So that means that position AJ is an anti-exceedance of W. So now let's suppose that J is not a descent in sigma of W. Then either AJ has to appear last in its cycle in standard notation, so if J is not a descent, it means that what comes after AJ is bigger. So it either could be a bigger letter in the same cycle, or it could be that we're at the end of the cycle in standard cycle notation, it's the next cycle that's bigger. So then either AJ appears last in its standard notation cycle, now if it appears last in its cycle notation, then we have AJ is less than or equal to W of AJ. So most of the time it's going to be less than the first element in its cycle. But if we have a one element cycle to begin with, then we have equality here. AJ is going to be equal to W of AJ because AJ is WAJ. So anyway, if it comes last in the cycle, AJ is definitely less than or equal to WAJ. So now if AJ doesn't appear last in its cycle, then it appears consecutively right before AJ plus 1. I'll leave these here. We have AJ and AJ plus 1 appearing consecutively in a cycle with, and we're assuming that J is not a descent. So AJ less than AJ plus 1, which is W of AJ. So these two cases gave us AJ less than or equal to W of AJ and AJ less than W of AJ. So in both cases, AJ can't be greater than WAJ. So in both cases, position AJ is not an anti-exceedance of W. So just to restate this, descents, ascents, exceedances, and anti-exceedances are all equidistributed on Sn. Now recall the distribution on S3 is 1, 4, 1. On S4, it turns out to be 1, 11, 11, 1. So after looking at these two, you might ask, well, is this distribution going to be palindromic for all n? That is it going to be the same backwards and forwards? In fact, it is. So this distribution is palindromic for all n. And the proof is that, maybe I'll write the proof above, it might be slightly longer than one line, although not much longer. So if we look at the number of permutations in Sn such that the permutation has k descents, that equals the number of permutations such that the permutation has k ascents. Well, that equals the number of permutations that have n minus 1 minus k descents. Since the number of descents in W plus the number of ascents in W equals n minus 1. So that means the distribution of descents is palindromic. It goes the same back and forward. And then because of this equidistribution, descents, ascents, exceedances, and anti-exceedances all have to have palindromic distributions. The end.